Hello and welcome to another episode of Chemistry. My name is Catherine. I'm a former high school chemistry teacher as well as textbook author, and all I want to do now is to share with you everything I know so you don't ever need me. Today, we're going to talk about the rates of reaction. Specifically, I want to go through stuff like talking about what impacts the rate of reaction and how do you actually get a reaction, describe how catalysts impact rate of reaction and other factors that affect it, as well as looking at an energy profile diagram to show you what that looks like when you have a catalyst and when you don't have a catalyst. Let's talk about collision theory. Before you can have a reaction occur, some criteria need to be satisfied. So back in the old day when you're doing year 7 or year 8 science, what you'll notice is you might put some reactions together and you just expect a reaction to happen, but that's not really how it works. So, according to collision theory, three main things need to occur in order for a reaction to even happen. Firstly, the particles need to collide, so the reactants need to actually smash into each other. Secondly, they need to do it in the right orientation. So then, even if they smash together, if they're not in the right orientation, nothing's going to happen. Another really important point is when they smack together, they need to make sure that they have enough energy to meet what we call the activation energy. The activation energy is just the energy required to break the bond so you can actually start having a chemical reaction. Now, this here is actually meant to be a little GIF, so I'm going to change my screen to show you what that actually looks like. You can see these particles colliding together, but not all of these collisions are actually resulting in you making something. And so, yes, not only do they have to collide, they have to do it at the right orientation. So some of these collisions didn't happen to have anything, but eventually enough of them will collide and a product will form. But they need to collide in the right orientation and also have enough energy to meet the activation energy. That's why you were seeing some of the collisions that were in this animation not even form anything. Okay. What can impact the rate of reaction? Essentially anything that can impact those main criteria, them colliding at the right orientation and with enough energy to meet the activation energy, can all impact how quickly. So rate is just saying how quickly it can occur in a certain amount of time. How quickly reactions can occur. So you can increase the number of collisions. You can also increase the amount of energy that these collisions actually have so enough energy so that they meet the activation energy. So for example, things like adding some heat, so increasing the temperature or decreasing the temperature, can have an impact on the rate of reaction. Surface area, so having a big block that looks like that or making it this pieces smaller can actually impact how quickly how quickly the reaction can occur because of the number of collisions that can occur between reactants. Something else is to actually try and force them to come together. So really you're pushing, let's say for example you've got particles in a balloon, you're pushing them closer, you're increasing the pressure, you're increasing the concentration so that you can actually impact the rate of reaction. And also, as well as, I think this was meant to be concentration, increasing or decreasing the concentration of the particles that you have here. Okay? And there's actually a few more that we're going to go through. So let's talk about temperature. Now, if you increase the temperature, what happens is you're going to increase the energy in the particles. When you increase the energy of the particles, they're going to move a lot quicker. So you can see here, hopefully you can see in this diagram, if we increase the temperature, these particles are starting to bing around the place a lot quicker. Therefore, the chances of them actually smacking into each other is probably more. So you're increasing the number of collisions. And not only are you doing that, you're making them go quicker, you're making them smack into each other more. Because they all have more energy, what happens is there's a larger proportion of collisions that will actually have enough energy to satisfy the activation energy. Now with that, as you can imagine, this all results in an increase in rate of reaction. Let's look at the flip side. Well, if I decrease the temperature, everything's opposite. You have less energy in the particles, they move a lot less, they collide a lot less, and they probably don't have enough energy to meet and satisfy the activation energy, which means when you decrease the temperature, you're going to decrease the rate of reaction. So just think about it in terms of collisions, energy, orientation. If you can impact those, you can impact the rate of reaction. Let's talk about surface area. Now, if you think about having a larger chunk, say for example, you've got a big piece of ice, big block of ice. I don't know if you guys have seen it, but some blocks of ice, especially when you go to Vietnam or something like that, which is where I'm from, they deliver in huge blocks of ice. I'm talking the whole box, but imagine how long that would take to melt. But if you would actually smack it and break it down into smaller pieces, it melts a lot quicker. Why? You've got more surface area that's actually exposed to the environment, heat, to actually cause it to melt. So same sort of thing when you're talking about chemical reactions. If you're exposing more of these areas to more reactants, essentially what you're doing is you're increasing the number of collisions between reactants. So if you have a larger chunk, you've got less surface area, which means fewer collisions at the surface of those reactants, which results in a decrease in rate of reaction. If you do it on the flip side and you make the particles smaller, you're exposing more of that reactant, so more of the ice. So smaller particles, more surface area exposed, which means more collisions, more reactants available to actually collide, which increases the number of collisions, which will then hopefully also increase the rate of reaction. Again, you're impacting the number of collisions. So one of those 3 criteria that we spoke about at the start when it comes to collision theory. Concentration. What does concentration mean? The amount of stuff in a given space. That's it. So if you have a higher concentration, you have more particles present in that same volume, which means that you're going to have more frequent collisions. If that's the case, you're going to increase the rate of reaction. Let's look at a lower concentration. If in a lower concentration, you have fewer particles in that same volume, fewer collisions as a result, because you've got less particles hanging around to actually collide with each other. As a result, you're going to decrease the rate of reaction. So if you have a look at this diagram here, same box, same volume. That's really important. You need to be comparing the same volume. That's why molarity for us is moles per liter, because we're looking at 1 liter. So looking at this, you can see that there's a higher concentration. In the same space, you've got more particles. Much more than the one on the right-hand side. So again, same space, but less particles. So you can imagine there are less particles to come and smack into each other, which makes it less likely for that to occur in a certain space of time, which means a lower rate of reaction. Why did I do this twice? Let's skip that. What about pressure? Now, firstly, what is pressure? So imagine each of these little guys are particles that are sitting inside your balloon. When you blow it up, make the balloon bigger. Now, the particles are trying to smack against the inside of that balloon. Pressure is just the force, the smacking of those particles, like pushing against the walls of the balloon, which is what I was trying to show here, which I think is really cute. So pressure is just the force acting on the wall. So if you've got more particles smacking into that same area, you've got a higher pressure. And on the flip side, lower pressure, lower particles. So if you increase the pressure, a way to do that is you make the space smaller. So if you have the same number of particles, you literally just go, you decrease the volume. By doing that, you've got more particles in that given space, which means you have an increase in concentration. The reason why I'm saying it like this is because we just learned about concentration. So if you can relate pressure and concentration, they kind of go hand in hand. If you decrease the pressure, how do you decrease the pressure? You make the volume bigger because you're giving them more space to move around, and the smacking against the walls occurs a lot less in that given space. So to decrease the pressure, you make the space bigger. If the space gets bigger, there's more room to move. There's less concentration. You're decreasing the concentration, so the particles in that given space, which means that there's less potentially collisions that are occurring because you've got more space, more to move around, less likely to hit something. So as we know, increasing the pressure or increasing the concentration, whichever way you want to say it, increases the rate of reaction. Whereas on the flip side, if you decrease pressure by making the volume bigger and the concentration decreasing, you're decreasing the rate of reaction. So have a look here. You've got this, say, how many particles here we got? So 9 particles in a smaller space. You can see that there's higher concentration, higher pressure. If I open that box and I expand the box a little bit with the same number of particles, much more space. So they're probably having less collisions in that same amount of time, which means that you're going to have a lower rate of reaction. Okay, so as we can see there, if we increase pressure, we're increasing concentration. If we increase concentration, chances are there's an increase in reaction rate. If I decrease pressure, I'm going to decrease the concentration, which means a decrease in reaction rate. Alrighty. What about when you have a catalyst? Catalysts are really interesting. In chemistry, we call them catalysts. In biology, you'll call them enzymes. It's just a biological catalyst. So if you do biology, you'll know what catalysts do. And that is they provide an alternative pathway for a reaction to occur. And that alternative pathway requires less energy. In other words, they're actually making the activation energy lower. Woohoo! What does that mean? That means that in that given environment, in that same temperature with the same number of particles, there's a higher chance that there are lots of particles that have enough energy. Because what you've done is, instead of the energy level being up here, you're going to decrease the energy level required for the bonds to break, for products to form. Which means that more of the particles within the system will probably have enough energy that when they smack into each other, they're going to have successful collisions. As a result, we're going to increase the rate of reaction. Cool. This is an example of catalytic converters, but I just wanted to use this as an example to show you how catalysts actually work. So catalysts, they provide a surface for the reactions to come and hang, be a little bit closer together. Some of these catalysts can actually help orientate the particles in a certain way, so it's more likely that when they do collide, a reaction will form. But also, depending on the catalyst that you have, they can play around with the bonds that are actually in each of the reactants, start to wiggle and start to break them already. So that lowers the actual energy required afterwards when you actually have these reactants interacting with each other. So a catalyst is really cool. The thing with catalysts is they don't get involved in the reaction. They provide a surface for the reaction to occur, but they don't take part in the reaction. So like enzymes, they're not used up. They provide a space, like the active site of an enzyme, for the substrates to come together, make the complex, and then form a product. If you look at it from an energy profile diagram, this is what it looks like. So if you've got A and B here, and you want to form AB, this is a normal energy profile diagram. So you can see how much energy is required. So this would be the activation energy for a reaction where you don't have a catalyst. Or let's call, instead of enzyme, let's call this catalyst. So have a look at the activation energy there. But as soon as you use an enzyme, you can see that the activation energy is a lot smaller, which means that more of those particles are most likely to have enough energy to actually, when they collide, form a product. So you can see here. All right, cool. But what you'll notice is the delta H, so the enthalpy of the reaction, does not change. The energy in the reactants and the energy in the products don't change. It's just the energy required to break bonds and then make product is a lot lower with a catalyst than without a catalyst. So if you look at this from a Maxwell-Boltzmann curve, let's draw an example of one. So this is number of particles or molecules, whatever you want, depends on what your reaction is. And this is energy. And let's just say we've got something that looks like this. Okay, it's a distribution because not all particles will have the same amount of energy in the same environment. Let's just say, reminder that the area under the curve is the total number of particles. So let's just say this is the activation energy in a normal reaction. So you can see here, only a small subset of reactants here have enough energy to actually meet the activation energy to form any products. But if I go along and I add a catalyst, what could happen is the activation energy here with the catalyst has decreased. So you can see that there's a greater area under the curve here that has enough energy to fulfill the activation energy products form. So depending on how you want to look at it, either energy profile diagrams or even look at Maxwell-Boltzmann curves, that's what it looks like. Let's go through an example. A lot of talk, let's go through an example. So here you have a graph that shows the volume of hydrogen gas produced over time in experiments. In both experiments, you've got plenty of hydrochloric acid and a fixed amount of zinc metal. You can see here. And the way that you would measure rate of reaction is you want to see how much stuff is produced in a certain amount of time. Most of the time this is going to be a gas, so the gas will form, you'll lose your mass, or you can actually measure the volume of gas. In this experiment, they're talking about measuring the volume of gas. We have to figure out what could explain the differences in what you see here. So you see you've got two reactions, you've got Q and you've got P. A few things for you to note here. You notice that over time, even though the graphs kind of start off different, they both end up in the same place. That means that they'll produce the same volume of hydrogen over time, which means that they don't vary in the amount of reactant that they have, right? Because you're making the same amount of product. So same hydrogen formed in terms of volume, same, let's go volume of hydrogen formed equals same amount of reactant, or you can say that same amount of limiting reagent. So you're making the same amount of stuff, right? So then we have to go and explain the main difference, and that is this part here. Why is it that Q is much lower than P? What can you say? Let's compare the rate of reaction. Let's just take some random time points. So just go, I don't know, say that's 1 minute. Let's say that's 2 minutes, whatever. So in 1 minute, you can see that, in 1 minute, I've got it in the wrong spot. 1 minute here, you can see that Q produces a smaller volume of hydrogen than P. What does that mean? That means that the rate of the reaction of P is actually higher. If we have a look at 2, so we go here. So this is at 2 minutes. This is how much volume of hydrogen is formed in reaction Q. But look at reaction P, it's a lot higher. So what we can see from this graph, the main difference here is saying that the rate of reaction for P is higher than Q. So, but however, they'll level off. So P starts to level off a lot quicker. Q takes a little bit longer, but they both end up in the same spot where they produce the same amount of volume, of hydrogen gas. So what could explain this? Let's have a look. So the zinc in the experiment was in powder form rather than large granules. I'm guessing this says granules. Is that possible? Now, if we have it in powdered form, what we're doing here, I don't like that. I'm going to change it to this color. If we have it in powdered form, what we're saying is we're increasing the surface area. That when we increase the surface area, what we're going to do is we're going to increase the rate of reaction. Is it true that P has a higher rate of reaction than Q? Yes, right? But making it powder doesn't mean that you're adding anything more. You're using the same quantity, you're just making the particles smaller, which means you'll get the same amount, the same volume of hydrogen being produced, but it's just quicker, which is exactly what this graph is showing. So the answer here would be A. But let's just go through some of the other ones. Catalyst was added to reaction mixture experiment Q. Now, if a catalyst was added, that means you're increasing the rate of reaction. Now, that doesn't seem like Q has a greater rate of reaction than P. It's the other way around, so it can't be B. Hydrochloric acid in Q had a higher concentration. If there was a higher concentration, that means that there would be an increase in the rate of reaction. Again, that graph doesn't show that. It shows the opposite, that P has a higher rate of reaction than Q. The pressure in Q, it was higher than P. Again, not right. Why? Because Q actually has a lower rate of reaction. If you increase the pressure, chances are you're going to increase the rate of reaction, so it can't be it. Let's go through one more worked example. You can see here 4 different experiments involving calcium carbonate chips and an acid. And what we do is we measure the volume of gas. You can see CO2 is the gas that will be formed here. In all of the experiments, the same quantity of of acid was used. So really what could vary, if anything, would be the calcium chips. We have to figure out based on the graph which of the statements is true. Reaction 4 used more calcium chips than reaction 2. So let's compare 4 and 2. Now, if you're going to use more calcium chips, you're going to produce more carbon dioxide, right? Given that the acid is the same, and let's assume that the acid isn't the limiting reagent. So if that's the case, then reaction 4 couldn't, because it's actually making less than 2, so it won't be that. Compared to reaction 1, reaction 2 used a catalyst. So look at 1 and 2. You can see that between the two, 1 has a higher rate of reaction, right? Faster rate of reaction than 2, because you're making a lot more stuff in the same amount of time. So that can't be right, because if it was using a catalyst, reaction 2 would actually have a higher rate of reaction, so it'd be quicker, greater rate of reaction, so it can't be right. Oh, looks like we might have 2 right answers here. Compared to reaction 3, reaction 4 occurred at a lower pressure. 3, maybe, here we go. You can see that there's a 4 has a lower rate. So if all you're doing is changing the pressure, 4 is just a lot slower. So it could be 4. It could be 4. Compared to reaction 1, reaction 2 occurred at a lower temperature. So have a look at that. Same, right? Compared to reaction 2 at a lower temperature. So it's possible that that's also the correct answer. It looks like this one has 2 options. So that's fine. Why? Because 2 is slower. Can you see the rate of reaction is lower? However, the amount of stuff you make is the same. By changing the temperature, you don't change the amount of stuff that you use in the reaction, so you should get the same stuff. It's just that you'll get there quicker. So 1 should have a higher temperature than 2, or 2 should be at a lower temperature than 1 because it happens a lot slower. So that's also correct. It's possible that C and D could be correct in this instance. So let's summarize everything that we've spoken about here. Reactions don't always occur just because you're putting reactants together. They need to meet some criteria. The particles need to collide. They need to collide at the right orientation and with enough energy to meet the activation energy. Anything that you do that can impact any of those criteria will impact the rate of reaction. So things like temperature, concentration, pressure, catalyst, surface area, all of those things can impact it because they can either impact the collision, they can impact the orientation, or they can also impact the amount of energy you need. Something that I didn't mention before, and if you've made it to the end of this, then I think you deserve this. Just because you have more particles colliding doesn't necessarily mean you have an increase in the rate of reaction. If you still don't have enough energy, it doesn't matter how much you collide, you won't have a reaction. You can have the right orientation every day of the week, but again, if you still don't have enough energy to meet the activation energy, no products will be made. No reaction will occur. All right. So Thank you for hanging out with me today. I hope this was useful for you. And always remember, no matter what anybody says, yeah, you can. Catch you next time.